Annapolis, Maryland, May 1945. Dr. Robert Goddard stood motionless in the Naval Laboratory warehouse, staring at the object before him. The ailing physicist, his voice already reduced to a hoarse whisper by the throat cancer that would claim him within months, ran his fingers along the cold aluminum skin of the German V-2 rocket. For 20 years, he had been America's lone voice in the wilderness of rocketry, building liquid-fueled rockets on shoestring budgets, while the government ignored his pleas for support. Now, in this dimly lit warehouse, surrounded by Army ordnance officers and Navy engineers, Goddard confronted a truth that would haunt American rocket science for the next decade. The Germans hadn't just built a rocket. They had built an entire industrial revolution in rocketry, and America had been asleep at the launch pad. What Goddard didn't know as he circled that 46-foot missile was that this examination would reveal a technological chasm so vast that American scientists would spend the next 15 years desperately trying to close it. The V-2 wasn't just ahead of American capabilities, it represented technologies that didn't exist in the United States, engineering solutions to problems American scientists hadn't even identified, and manufacturing precision that American factories couldn't replicate. The rocket sitting in that warehouse was proof that while America had Robert Goddard, Germany had Peenemünde, a sprawling research complex with thousands of scientists, unlimited funding, and a 7-year head start on weaponized rocket technology that would reshape the future of warfare and space exploration. The story of how America discovered it was years behind in rocket technology begins not in 1945, but in April, when American forces racing across Germany stumbled onto something that would change the trajectory of human history. April 11, 1945, the Harz Mountains, Germany. Soldiers of the United States 3rd Armored Division descended into the Mittelwerk underground factory complex near Nordhausen, expecting to find another German weapons facility. What they found instead was an industrial operation on a scale that defied comprehension. Tunnels carved deep into the mountains stretched for miles. Production lines contained partially assembled V-2 rockets at various stages of completion. Components filled warehouses, technical documents stacked in rooms. And everywhere, evidence of forced labor. Emaciated prisoners from the Mittelbau-Dora concentration camp, some barely alive, who had been enslaved to build Hitler's vengeance weapons. Major James Hamel of Army Ordnance walked through those tunnels with growing disbelief. The Germans had been producing V-2 missiles at a rate of 600 per month. Each rocket required 50,000 individual parts. The precision machining, the quality control, the logistics of moving components through those underground production lines, it represented an industrial achievement that seemed impossible for a nation supposedly on the brink of defeat. But Hamel understood something the infantry soldiers didn't. These weren't just weapons. They were the key to the future. The Soviet Union's occupation zone was scheduled to begin in weeks. Everything in this facility, every document, every component, every rocket, it would fall into Stalin's hands unless the Americans moved fast. Within hours, Colonel Holger Toftoy received urgent orders from Washington. Get the rockets, get the documents, get them out before the Soviets arrive. What followed was Special Mission V-2, one of the most critical intelligence operations of the war's final days. American troops worked around the clock loading railway cars. 341 rail cars filled with V-2 components, enough hardware to build approximately 100 complete rockets. Technical documents weighing tons, all of it racing against time toward the port of Antwerp, where Liberty ships waited to carry America's captured prize across the Atlantic. By late May, the first components arrived at the White Sands Proving Ground in New Mexico's Tularosa Basin. Army engineers began cataloging what they'd captured, and with each crate they opened, with each technical drawing they examined, the magnitude of German achievement became clearer and more disturbing. The V-2 rocket, designated Aggregate 4 by its creators, was 46 feet tall and weighed nearly 28,000 pounds at launch. It could carry a 1-ton warhead 200 miles with reasonable accuracy, but these basic specifications, impressive as they were, told only part of the story. The real revelation came when American engineers began disassembling the rocket to understand how it worked. The engine sat at the base, a massive combustion chamber capable of producing 60,000 pounds of thrust. To American engineers familiar with Goddard's work, this number was staggering. Goddard's largest rocket engine had achieved 985 pounds of thrust after years of experimentation. The Germans had created an engine 60 times more powerful, and they were mass-producing it. Dr. Theodor von Karman, director of the Jet Propulsion Laboratory at Caltech, was among the first American scientists to examine the V-2 in detail. His team had been developing rocket technology for the Army since 1942, working on what would become the Corporal missile. When von Karman saw the V-2's propulsion system, his reaction was blunt. "We are at least 7 years behind." The propulsion system alone represented multiple technological breakthroughs. The combustion chamber used a double-wall design. Alcohol fuel flowed through the outer jacket before entering the chamber, simultaneously cooling the chamber walls and preheating the fuel. This regenerative cooling solved one of rocketry's fundamental problems, preventing the chamber from melting under the extreme temperatures of combustion that reached 5,100 degrees Fahrenheit. But it was the turbo pump that truly shocked American engineers. At the heart of every V-2 sat a steam-driven turbine that spun at 4,000 revolutions per minute, powering centrifugal pumps that forced fuel and liquid oxygen into the combustion chamber at 125 liters per second. The turbine itself produced 600 horsepower, driving pumps that had to handle cryogenic liquid oxygen at minus 297 degrees Fahrenheit while operating at pressures that would destroy conventional pumps. American engineers stared at this device with a mixture of admiration and despair. The turbo pump represented 7 years of German development incorporating metallurgy, precision machining, and engineering solutions that didn't exist in American industry. The turbine blades were forged from nickel-chromium alloys that could withstand both extreme temperatures and rotational forces that would tear apart lesser materials. The pumps featured seals that prevented cryogenic liquid oxygen from leaking while spinning at speeds where any imbalance would cause catastrophic failure. Lieutenant Commander Robert Truax, a Navy engineer who examined the V-2's propulsion system, wrote in his report, "The German turbopump is not simply ahead of American technology. It is technology we do not possess. Building a duplicate would require developing new alloys, new casting techniques, new manufacturing processes. We estimate 18 months minimum to create a single working prototype, assuming unlimited funding and access to materials currently unavailable due to post-war shortages." Then came the guidance system, and with it another revelation of how far behind America had fallen. The V-2 used an analog computer called the Mischgerät, developed by Helmut Hölzer, that integrated inputs from gyroscopes and accelerometers to control the rocket's flight. 2 free gyroscopes, one for pitch and one for yaw and roll, constantly measured the rocket's orientation. A pendulous integrating gyroscopic accelerometer, the first of its kind, measured acceleration and integrated it over time to calculate velocity. When the rocket reached its programmed velocity, typically around 3,500 miles per hour, the guidance system cut off the engine. The sophistication of this system stunned American engineers. The gyroscopes were manufactured by Kreiselgeräte with precision that American firms couldn't match. The analog computer processed multiple inputs in real time, sending signals to 8 control surfaces, 4 external rudders on the tail fins, and 4 graphite vanes in the rocket's exhaust stream. These vanes, positioned directly in the rocket's jet stream at temperatures exceeding 5,000 degrees, were made of graphite that could withstand the heat while providing steering control during the critical first 60 seconds of flight. Dr. Charles Stark Draper of MIT, America's leading expert in guidance systems, examined the V-2's controls with professional respect. Draper had spent years developing gyroscopic instruments for aircraft and submarines. When he saw the German system, he immediately recognized innovations his laboratory hadn't conceived. "They solved the integration problem," Draper noted in his technical assessment. "They created an accelerometer that doesn't just measure force, but calculates velocity by integrating acceleration over time. This is the first fully electronic active control system ever deployed on any vehicle. It's essentially a fly-by-wire system decades ahead of anything in aviation. But perhaps nothing revealed the technological gap more clearly than the manufacturing quality. American engineers examining V-2 components found precision machining that exceeded peacetime commercial standards. Welds were perfect. Tolerances were measured in thousandths of an inch throughout. Components that experienced high stress were overbuilt with safety margins that American designers, constrained by material shortages, would never specify. An Army ordnance officer examining the turbopump assembly noted, "Every component appears designed to survive worst-case scenarios. The Germans built for reliability under combat conditions. The fuel lines include redundancy we would consider wasteful. The electrical system has more circuit breakers than necessary. The structure is heavier than optimal weight calculations would require. This is engineering from a nation with resources to build things right, not engineering from a nation scrambling to build things cheap." The electrical system alone represented sophistication beyond American practice. The V-2 used a 24-volt architecture with generators driven by both the main turbopump and a separate auxiliary turbine. American rockets, when they used electrical systems at all, employed 12-volt designs with single generators. The V-2's electrical harness contained 8 miles of wiring, all carefully routed, bundled, and protected. The system included motor-driven valves, gyroscope power, ignition systems, and telemetry equipment that could transmit flight data in real time. When Robert Goddard examined the V-2 that May afternoon in Annapolis, he saw immediately that many features paralleled his own work. Liquid oxygen and alcohol as propellants, turbine-driven centrifugal pumps, gyroscopic stabilization, blast vanes for steering. In a letter to his patron, Harry Guggenheim, Goddard wrote with barely concealed bitterness, "The Germans have used my patents. They have taken concepts I developed and built them at a scale I could never achieve. The V-2 is what my rockets could have become if anyone in America had listened." But Goddard, for all his brilliance, missed the crucial distinction that other American engineers immediately grasped. The Germans hadn't stolen American technology. They had developed an entirely independent rocket program that, by 1945, exceeded American capabilities by nearly a decade. Hermann Oberth's theoretical work in Germany paralleled Goddard's. Wernher von Braun's team at Peenemünde had begun liquid-fuel rocket experiments in 1932, building on their own research tradition. By 1934, their A-2 rocket had already exceeded Goddard's highest altitude. The German program had state funding, military priority, access to Germany's finest technical universities, and the labor of thousands of scientists and engineers from every discipline. Goddard's highest altitude was 9,000 feet, achieved in 1937. The A-4 routinely reached 50 miles altitude, crossing into space, before arcing down toward its target 200 miles away. Goddard's most powerful engine produced 985 pounds of thrust. The V-2 engine produced 60,000 pounds. Goddard worked with a handful of assistants in the New Mexico desert, funding from the Guggenheim Foundation, and indifference from the U.S. military. The Germans worked at Peenemünde, a sprawling facility that consumed resources equivalent to America's Manhattan Project. The comparison wasn't between American technology and German technology. It was between one brilliant physicist working essentially alone and an entire nation's industrial and scientific establishment focused on rocket development as a military priority. By June 1945, as American engineers continued examining captured V-2s, a consensus emerged in classified reports circulating through the War Department. The United States faced a critical strategic vulnerability. Rocket technology would define future warfare. The Germans had proven that ballistic missiles could strike targets hundreds of miles away with no defense possible. The Soviet Union had captured Peenemünde, the V-2 production facilities, and thousands of German rocket technicians. Unless America acted decisively, the post-war world would find the United States hopelessly behind in the most important military technology of the emerging era. This assessment led directly to Operation Paperclip, one of the most controversial decisions of the immediate post-war period. In September 1945, Wernher von Braun and 126 German rocket scientists arrived at Fort Bliss, Texas, under military custody. These men had built Hitler's vengeance weapons. Many had used slave labor from concentration camps. Their rockets had terrorized London and Antwerp, but they possessed knowledge that America desperately needed. The moral complexity of this decision troubled many Americans. These were Nazi scientists, some with SS ranks, responsible for weapons that took thousands of civilian lives. The prisoners who built the V-2s at Mittelwerk died in greater numbers than the rockets themselves caused, worked to exhaustion in the underground factories. Yet the Cold War was beginning, and the Soviet Union had already begun rebuilding the German rocket program under Helmut Gröttrup, capturing their own contingent of German engineers. At White Sands Proving Ground, work began assembling captured V-2s for test launches. The first static test firing occurred March 15, 1946. The first launch followed April 16. At 2:47 in the afternoon, the reassembled German rocket lifted off from the New Mexico desert. The guidance system failed almost immediately. A fin separated. The rocket reached only 3.4 miles altitude before crashing. It was a humbling demonstration that even with German rockets and German scientists, America still had much to learn. Colonel Harold R. Turner, observing that first failed launch, remarked to his staff, "We have the hardware, we have the men who designed it, but we don't have the industrial infrastructure that built it, the experience base that developed it, or the knowledge that comes from 6,000 launches. The Germans conducted that many test firings and combat launches. We're starting from zero." Over the following years, 67 captured V-2s were launched from White Sands, with mixed success. 68% were considered successful, a failure rate that would have been catastrophic in combat. Each launch taught American engineers lessons about rocket propulsion, guidance systems, high-altitude flight dynamics, and the engineering challenges of ballistic missiles. Scientists from universities, military laboratories, and emerging aerospace companies sent experiments aloft on V-2s. instruments to measure cosmic radiation, cameras to photograph Earth from space, sensors to sample the upper atmosphere. On October 24, 1946, a V-2 carried a 35mm camera to 65 miles altitude, capturing the first photographs of Earth from space. The images, grainy black and white pictures showing the curvature of the planet, represented a historic first. They also demonstrated what German technology had achieved: the ability to send payloads beyond Earth's atmosphere and return useful data. But using captured German rockets was never the end goal. It was merely the bridge to developing American rocketry. In 1948, the Army Ordnance Department selected Redstone Arsenal in Huntsville, Alabama, as a permanent rocket research center. Wernher von Braun and his team moved there, joined by American engineers, to begin developing missiles based on V-2 technology but adapted to American needs and capabilities. The first major American rocket to emerge from this collaboration was the Redstone, a direct descendant of the V-2. First tested in 1953, the Redstone incorporated V-2 principles: liquid oxygen and alcohol propellants, turbopump fuel delivery, gyroscopic guidance, but it also incorporated improvements: better fuel efficiency, more reliable guidance, American manufacturing processes adapted to rocket production. By the mid-1950s, the technological gap was finally closing. American engineers had learned from German designs, then moved beyond them. The Jupiter, Thor, and Atlas missiles represented indigenous American rocket technology, built by American companies using American materials and manufacturing techniques. When the Soviet Union launched Sputnik in October 1957, America responded with Explorer Köln in January 1958, launched on a Jupiter-C rocket derived from Redstone technology. The Saturn V moon rocket that would carry Americans to the lunar surface in 1969 was designed by Wernher von Braun's team at NASA's Marshall Space Flight Center. Its F-1 engines produced 1.5 million pounds of thrust, each 25 times more powerful than the V-2. But the technological lineage was clear: regenerative cooling, turbopump fuel delivery, gimbal-mounted engines for thrust vectoring, sophisticated guidance systems. All concepts proven in the V-2, now scaled and refined to achieve what Goddard had once dreamed and what the Germans had made seem possible. Looking back from the 21st century, the V-2's legacy is complex and troubling. It was a weapon of terror that achieved little military value at enormous cost in resources and lives. The slave labor that built it represents one of World War II's many atrocities, yet it was also the world's first practical ballistic missile, the first object to reach space, and the technological foundation for everything that followed in rocketry and space exploration. For American scientists examining those first captured V-2s in 1945, the experience was humbling. The United States, with its vast industrial capacity and scientific talent, had been years behind a nation it had just defeated in war. Robert Goddard's pioneering work had been ignored by his own government while Germany invested billions in developing similar technology at scale. The lesson was clear and would shape American military and scientific policy for decades. Technological superiority requires sustained investment, institutional support, and recognition that individual brilliance, however remarkable, cannot substitute for organized national effort. When NASA dedicated the Goddard Space Flight Center in May 1959, Administrator T. Keith Glennon acknowledged both the American pioneer and the uncomfortable truth his career revealed. Robert Goddard dreamed of rockets that could reach the moon. He built rockets that reached 9,000 feet. The Germans, working independently, built rockets that reached space. Today, America's space program builds on both legacies, but also on the lesson that genius requires support, vision requires resources, and leadership in technology demands national commitment. In the end, the V-2 taught America three critical lessons. First, that rocket technology would define military power and open access to space. Second, that technological leadership could be lost through neglect and regained only through sustained effort. Third, that in the emerging Cold War, the nation that controlled the high ground of space and the long reach of ballistic missiles would hold strategic advantage. American scientists examining that first captured V-2 in May 1945 saw all of this, even if they couldn't yet articulate it fully. They saw the gap between where America was and where it needed to be. They saw the cost of ignoring visionaries like Goddard. They saw the future captured in German hardware, waiting to be understood, absorbed, and ultimately exceeded. The warehouse in Annapolis where Robert Goddard examined the V-2 is long gone. But the rocket he saw that day, and the technological revelation it represented, changed the course of American history. From that moment of recognition, that understanding of how far behind America had fallen, came the determination to catch up, the investment in rocket science, and ultimately the achievement that would place American footprints on the moon just 24 years later. The V-2 was Germany's vengeance weapon. For America, it became something else entirely, a wake-up call, a teaching tool, and a challenge to do better. The fact that Americans did eventually surpass what the Germans had achieved, building rockets that carried humans beyond Earth orbit, proved that technological gaps can be closed, but it requires recognizing the gap exists, committing the resources to close it, and understanding that in technology as in war, those who fail to invest in the future will be overtaken by those who do. When Wernher von Braun stood at Cape Canaveral in July 1969, watching Apollo 11 launch toward the moon atop a Saturn V rocket, he reflected on the path from Peenemünde to the Sea of Tranquility. "We always knew it was possible," he said. "The physics were clear even in the 1930s. What changed was not the science, but the commitment. America in 1969 could do what Germany in 1945 could not: focus the resources and will of an entire nation on reaching beyond Earth, not as a weapon, but as an achievement of the human spirit." That commitment began in warehouses where American engineers examined captured German rockets and confronted an uncomfortable truth: they were years behind. The question was whether they had the determination to catch up. History records that they did.